August 7th, 1942. 0214 hours. Guadalcanal. Private first class. Eugene Sledge could not see a damn thing beyond the edge of his foxhole. The jungle was black, not dark. Black. The kind of black that made you wonder if you still had eyes. He pressed his body against the wet earth and tried to control his breathing. His hands found the rifle beside him. An M1 Garand. 9.5 pounds of wood and steel that he had fired exactly twice since landing on this god-forsaken island 16 hours ago. Both times at coconut trees during practice. Now he was about to find out if the weapon worked as advertised. The Japanese came without warning. 1 second there was silence. The next second, the jungle exploded with screaming and rifle fire and the wet smacking sound of bullets hitting dirt. Sledge saw muzzle flashes, 30 yards out, maybe less. His rifle came up without conscious thought, finger on trigger, squeeze. The M1 kicked against his shoulder. The report was deafening. But something else happened that Sledge was not expecting. The rifle had already loaded itself. The bolt had cycled back, ejected the empty brass, stripped a fresh round from the clip, and chambered it. All of this in a fraction of a second. Sledge squeezed the trigger again, and again, and again. 8 rounds in the time it took him to exhale. He heard a metallic ping as the empty clip ejected itself. His hands were already reaching for a fresh one. 3 seconds later, he was firing again. 20 yards to his left, Corporal Robert Leckie was doing the same thing. Fire, 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 ping, reload, fire, fire, fire. The 2 Marines were putting rounds downrange so fast that the Japanese assault line faltered, stopped, began to fall apart. Across the perimeter, dozens of other M1 Garands were hammering out the same rhythm. The volume of fire was something out of a fever dream. It did not sound like rifles. It sounded like machine guns. Out in the jungle, Sergeant Takeshi Yamamoto threw himself behind a fallen log and tried to make sense of what was happening. He had fought the Chinese in Manchuria. He had fought the British in Malaya. He knew what rifle fire sounded like. But this was different. This was continuous. This was impossible. The Americans were using automatic weapons. They had to be. Nothing else could explain the sheer volume of incoming fire. Yamamoto carried a Type 38 rifle. It was a good weapon, accurate out to 500 meters, light, reliable. But it was a bolt action. Every single shot required him to pull back the bolt handle, eject the spent cartridge, push the bolt forward, chamber a new round, lock the bolt down, reacquire his target, then fire again. 4 seconds at a minimum. 4 seconds during which the Americans were firing 3 more times. Yamamoto rose from behind the log. He had his orders. He took 3 steps forward, and a bullet from Sledge's M1 Garand hit him in the upper chest. The impact spun him sideways. He hit the ground and did not get up. His last thought was not about his family, or his emperor, or his honor. His last thought was a simple calculation. 1 American rifleman equals 4 Japanese riflemen. We are going to lose this war. The battle lasted until dawn. When the sun finally rose over the blood-soaked jungle, Captain James Russell walked the perimeter and counted bodies. 143 Japanese dead in front of the Marine positions. The Marines had lost 11 men. Russell had expected casualties 3 times that number. He had been at Wake Island. He had seen what Japanese infantry could do in a night assault, but this was different. The M1 Garand had changed the mathematics of combat. Russell filed his after-action report that afternoon. He used language that was deliberately understated because he knew nobody back at headquarters would believe him otherwise. The weapon exceeded expectations. Enemy assault waves broke down under sustained fire. Recommend immediate deployment to all infantry units. What Russell did not know was that his report landed on a desk in Washington at the same moment that similar reports were arriving from 6 other Marine companies on Guadalcanal. The pattern was unmistakable. American units armed with M1 Garands were achieving casualty ratios between 8-1 and 12-1 against Japanese forces. These numbers were so far outside normal combat statistics that the War Department initially suspected the reports were fabricated. They were not. The M1 Garand was doing exactly what it had been designed to do. It was giving American infantrymen a firepower advantage so overwhelming that it was changing the fundamental nature of infantry combat. But the road to Guadalcanal had been long and brutal. The M1 Garand did not appear overnight. It was the product of 20 years of failure, frustration, and one man's absolute refusal to accept that the problem could not be solved. That man was John Cantius Garand. He was nobody special. He was born in Quebec in 1888. He came to the United States in 1898 at age 11. He spoke English with a French-Canadian accent his entire life. He had no engineering degree, no formal training. What he had was an intuitive understanding of how metal parts moved under stress and a work ethic that his co-workers described as bordering on psychotic. In 1919, the United States Army Ordnance Department issued a challenge to American firearms designers. Design a self-loading rifle that fires a full-power cartridge, survives battlefield conditions, and costs less than $100 to manufacture. Every major firearms company in America tried. Winchester submitted a design in 1920. It jammed after 200 rounds. Remington submitted a design in 1922. It weighed 14 pounds. Thompson Auto Rifle Company submitted a design in 1924. It cost $300 per unit. By 1928, the Ordnance Department was ready to give up. The consensus among experts was that a self-loading battle rifle was technically impossible. The recoil forces were too violent, the mechanisms too complex, the tolerances too tight. Garand did not care about expert consensus. He worked alone in a cramped workshop at Springfield Armory in Massachusetts. He did not have a team of engineers. He did not have computer models or advanced metallurgy labs. What he had was a lathe, a milling machine, a pile of steel stock, and an almost supernatural ability to visualize how mechanical systems would behave under load. He started with the fundamental problem. A rifle cartridge generates 50,000 pounds per square inch of pressure when it fires. That pressure has to go somewhere. Most self-loading designs use that pressure to blow the bolt backward, but the forces involved were so violent that they destroyed the locking mechanism after a few hundred shots. Garand's insight was brilliant in its simplicity. Instead of using all that pressure to move the bolt, he would tap off just enough gas to operate a piston. The piston would unlock the bolt. Only then would the bolt move backward under spring pressure to eject the spent case and load a new round. The concept was elegant. The execution was hell. Garand spent 6 years getting the gas port dimensions right. Too large and the rifle cycled too fast and beat itself apart. Too small and it did not cycle at all. He needed a port that was 0.047 inches in diameter. No larger, no smaller. The problem was that his measuring tools could only measure to 0.005 inches. He was trying to hit a tolerance that was 10 times finer than his instruments could detect. He did it by feel. He would drill a port, test fire the rifle, watch how the brass ejected. If the brass flew out more than 6 feet, the port was too large. If the brass barely cleared the ejection port, it was too small. He needed the brass to land exactly 4 feet away. It took him 4,000 test firings to get it right. In 1932, the Army ran acceptance trials. They took Garand's rifle and tried to break it. They fired 20,000 rounds through a single rifle without cleaning it. The rifle kept working. They buried it in sand. They soaked it in salt water. They froze it and baked it and dropped it from the back of a moving truck. The rifle kept working. On January 9, 1936, the United States Army officially adopted the M1 Garand as the standard service rifle. America became the first nation in history to issue a semi-automatic rifle to its entire infantry force. Germany would not field a comparable weapon until 1943, and even then only in limited numbers. The Soviet Union tried with the SVT-40, but abandoned it due to reliability issues. Britain stuck with bolt-action Lee Enfields throughout the entire war. Japan never even attempted to develop a semi-automatic infantry rifle. The Type 38 that Sergeant Yamamoto died carrying was a design from 1905. Literally the same rifle his father had used against Russia. But adoption was just the beginning. The real challenge was production. In 1936, Springfield Armory could produce maybe 200 M1 Garands per month. The Army needed hundreds of thousands. In 1940, with war looming in Europe, the War Department brought in Winchester Repeating Arms Company. By 1941, combined production hit 5,000 rifles per month. Then Pearl Harbor happened. Overnight, the production target jumped to 50,000 rifles per month. This required a complete retooling of American manufacturing. Every part had to be made to tolerances measured in thousandths of an inch. The barrel had to be straight to within 0.001 inches over its entire length. The gas port had to be exactly 0.047 inches. The bolt lugs had to lock with zero wobble. Parts that did not meet spec were scrapped. No exceptions. The rejection rate in early 1942 was 30%. By the end of 1942, it was down to 3%. American manufacturers had learned to work to precision tolerances that no other nation could match. The production numbers told the story. 1942, 450,000 M1 Garands. 1943, 1.3 million. 1944, 1.6 million. By the end of 1945, the United States had manufactured 5.4 million M1 Garands. To put that in perspective, Germany produced 400,000 Gewehr 43 semi-automatics during the entire war. The Soviet Union produced 1.6 million SVT-40s before giving up on them. Britain produced 0. Japan produced 20,000 Type 5 rifles, and they were so unreliable that Japanese troops refused to use them. The impact on combat effectiveness was immediate and measurable. Marine units on Guadalcanal reported that Japanese night attacks, which had been devastatingly effective in the Philippines, now broke apart under American fire. Army units in North Africa reported that German infantry armed with Kar 98K bolt actions could not sustain firefights against American infantry. Paratroopers in Sicily reported that they could hold defensive positions against numerically superior Italian forces because of superior rate of fire. The mathematics were brutal. One American rifleman with an M1 Garand could put 40 rounds downrange per minute. One German with a Kar 98K could put maybe 15. One Japanese soldier with a Type 38 could put maybe 10. This meant that an American infantry squad with 8 M1 Garands had the firepower of 24 German riflemen or 32 Japanese riflemen. But firepower was only part of the story. The M1 allowed soldiers to maintain their sight picture while firing. Bolt-action rifles required the shooter to look down at the weapon to work the bolt. Those 2 seconds of looking away meant losing your target. With the M1, soldiers could fire, observe where the shot went, adjust their aim, and fire again without ever taking their eyes off the target. This led to dramatically higher hit rates. Post-war studies showed that M1 equipped infantry achieved first-round hit probability of 42% at 100 yards. Bolt action equipped infantry achieved 23%. That difference was the gap between hitting your target and missing it, between living and dying. By late 1942, word of the M1's capabilities had reached Japanese military intelligence. They knew American troops were equipped with semi-automatic rifles. They knew these rifles were giving American infantry a massive advantage. What they did not know was how the rifles worked, or whether Japan could manufacture something similar. Japanese commanders urgently requested more information. On March 15, 1943, a Japanese reconnaissance patrol on Bougainville found 3 abandoned M1 Garands in a hastily evacuated American position. The rifles were immediately shipped to Tokyo Army Technical Bureau for analysis. The man assigned to lead the evaluation was Major Kijiro Nambu. He was one of Japan's most experienced firearms designers. He had created the Type 14 pistol. He understood weapons. He understood manufacturing. What he was about to discover would shake him to his core. Nambu locked himself in his workshop and began the disassembly. The first thing that struck him was the weight, 9.5 pounds. Light for a semi-automatic. Too light. How were the Americans controlling the recoil forces? He removed the wood furniture and exposed the action. What he saw made him stop breathing. The gas system, the rotating bolt, the operating rod, every component machined to impossible tolerances. He pulled out his micrometer and began measuring. The gas port was 0.047 inches in diameter. Perfect. Not 0.046. Not 0.048. 0.047. He measured the bolt lugs. 8 contact points, each mating surface flat to within 0.0005 inches. He measured the receiver. The rails were parallel to within 0.001 inches over the entire length. These were not normal manufacturing tolerances. These were precision instrument tolerances. The Americans were building rifles the way Japan built optical instruments. Nambu spent 3 days measuring every dimension. Then he spent another week testing the rifle. 2,000 rounds without cleaning, 0 malfunctions. He field stripped the weapon, buried it in sand, reassembled it, and fired another 1,000 rounds. 0 malfunctions. He soaked it in salt water overnight, dried it, fired 500 rounds, 0 malfunctions. The rifle was not just good, it was perfect. And that perfection terrified him, because Nambu knew something that nobody else in Tokyo wanted to admit. Japan could not build this rifle, not now, not ever. The tooling did not exist. The skilled machinists did not exist. The quality control systems did not exist. Japanese arsenals could hold tolerances to 0.01 inches on a good day. The M1 required 0.001 inches. That was a 10-fold difference. It might as well have been the difference between a bicycle and an airplane. Nambu wrote his report on March 28, 1943. He tried to be diplomatic. He used careful language. But the conclusion was unavoidable. The M1 Garand represents a 20-year technological gap in manufacturing capability. Recommend immediate revision of infantry doctrine to account for American firepower advantage. Do not attempt to copy this weapon. We lack the industrial capacity to produce it in meaningful numbers. His report landed on the desk of General Hideki Tojo 3 days later. Tojo read it once, read it again. Then he threw it in a drawer and never spoke of it again, because the alternative was too terrible to consider. The alternative was admitting that Japan had already lost the war, not because of strategy or tactics or fighting spirit, but because American factory workers in Springfield, Massachusetts and New Haven, Connecticut could hold tolerances to 1/1000th of an inch, and Japanese factory workers could not. By the end of 1943, every American rifleman in every theater of war carried an M1 Garand. By the end of 1944, the United States had produced enough M1 Garands to equip every infantryman in the Army and Marine Corps with 2 rifles each. By the end of 1945, the production total exceeded 5.4 million. The M1 Garand had become the most manufactured semi-automatic rifle in human history. More importantly, it had given American infantry a technological advantage that no enemy could match. General George S. Patton called it the greatest battle implement ever devised. He was not exaggerating. The M1 Garand changed infantry combat forever, and it all started with one man, working alone in a cramped workshop, refusing to accept that the problem could not be solved. April 2nd, 1943. Tokyo Army Technical Bureau. Major Kajiro Nambu's hands would not stop shaking, not from cold. His workshop was warm, not from fear. He had faced enemy fire in China. His hands were shaking because the micrometer in front of him was showing a number that meant Japan had already lost the war. 0.047 inches. The gas port on the American M1 Garand rifle was drilled to exactly 0.047 inches in diameter. Not 0.046, not 0.048, 0.047. Perfect. And Nambu knew with absolute certainty that every single M1 Garand produced in America had that exact same measurement. Japan could not do this. Japan would never be able to do this. 3 weeks earlier, Lieutenant Hiroshi Watanabe had found 3 M1 Garands in an abandoned American position on Bougainville Island. The rifles were caked with mud and jungle rot. The Americans had pulled out so fast they left their weapons behind. Watanabe picked one up. Heavy, solid. He worked the action. It moved like it was gliding on ice. Smooth. Too smooth. Japanese rifles had resistance when you worked the bolt. This felt wrong. Watanabe looked at his sergeant and said 5 words that would change everything. Pack these up. Command needs this. 2 weeks later, those 3 rifles arrived in Tokyo in a wooden crate. The entire bureau knew what was inside. The Americans had a semi-automatic rifle. Reports had been coming in from Guadalcanal for 8 months. Japanese infantry getting shredded by American fire. Casualty ratios that made no sense. 12-1, 15-1. Some reports claimed 20-1. Nambu had dismissed them as exaggerations, frightened soldiers overestimating enemy capabilities. Now he was about to find out if the reports were real. He pried open the crate. The rifles were still caked with mud. He pulled one out and set it on his bench. 9.5 pounds. Light for a semi-automatic. Too light. How were the Americans controlling the recoil forces? He began the disassembly. The trigger group came out as a single unit. 1 pin. The entire fire control mechanism dropped into his hand. Nambu had designed the Type 14 pistol. He understood modular design. But this was different. This was designed for field repair. A soldier could swap out the entire trigger group in under a minute without tools. Japanese rifles required an armorer and a full workbench to do the same repair. Nambu set the trigger group aside and kept working. The bolt came next. He slid it out of the receiver and stopped breathing. 8 locking lugs. Not 2 like a Mauser. Not 3 like a Lee Enfield. 8. Each lug was machined to mate perfectly with its corresponding recess in the receiver. Nambu pulled out his micrometer. He measured the first lug. 0.873 inches. He measured the second lug. 0.873 inches. Perfect. Must be lucky. He measured the third lug. 0.873 inches. His hand started shaking. He measured the fourth lug. 0.873 inches. Fifth lug. 0.873 inches. Sixth. Seventh. Eighth. Every single lug was 0.873 inches. Not 0.872. Not 0.874. 0.873. The tolerance was less than 0.001 inches. Nambu set down his micrometer and forced himself to breathe. His workshop was silent, except for the sound of his own heartbeat. 8 lugs, 8 perfect measurements. This was not quality control. This was something else. This was a nation that could manufacture precision on a scale that Japan could not comprehend. He thought about the factories back home, workers filing parts by hand, inspectors eyeballing tolerances, managers accepting anything that looked close enough. The Americans were not eyeballing anything. They were measuring to 10 times tighter than Japan's best arsenals, and they were doing it on millions of rifles. Nambu had been machining firearms for 20 years. He knew what .001-inch tolerance required. Temperature-controlled workshops, precision grinding machines, hardened steel cutting tools, quality control systems that rejected anything outside spec. Japan had none of these things. Japanese arsenals worked with hand files and visual inspection. They could hold tolerances to maybe .01 inches on a good day. The Americans were working 10 times tighter than that. The gap was not small. The gap was a chasm. And that chasm meant Japan was going to lose the war. He spent the next 4 hours measuring every dimension of the rifle. The gas port was .047 inches in diameter. Perfect circle. No tooling marks. The receiver rails were parallel to within .001 inches over their entire length. The chamber was reamed to exactly .005 inches oversize compared to the cartridge. Every measurement was perfect. Every tolerance was impossibly tight. Nambu pulled out his notebook and started calculating what it would take to manufacture this rifle in Japan. The numbers made him sick. They would need to retool every factory, retrain every worker, import precision machines from Germany, if Germany had them, which they probably did not. The timeline was 5 years minimum, more likely 10, and that assumed Japan was not fighting a war while trying to rebuild its entire manufacturing infrastructure. On April 5th, Nambu began function testing. He mounted the rifle in a test fixture and fired it. The action cycled. Bolt went back. Empty case ejected. New round loaded. Bolt locked. Total cycle time was .2 seconds. He fired again. Same result. He fired 200 rounds without pause. The rifle kept working. The barrel was hot enough to boil water, but the action kept cycling without hesitation. Nambu had seen Japanese prototype semi-automatics seize up after 50 rounds. This rifle had fired 200 without cleaning and showed no signs of stress whatsoever. He ran the weapon through the full battery of tests. Mud test. He packed dirt into every crevice of the action, closed the bolt, fired it. The rifle worked. Sand test. He dumped a handful of sand into the receiver, fired it. The rifle worked. Salt water test. He soaked the rifle in seawater overnight, pulled it out dripping, dried it with a rag, fired it. The rifle worked. Nambu was not testing anymore. He was torturing the weapon, trying to find its breaking point, trying to prove that American manufacturing was not actually superior, that there was some weakness he could exploit, some flaw in the design that would give Japan hope. After 3 days of abuse, he finally found one. He fired 1,500 rounds without cleaning. The gas piston rings wore out. The rifle began short-stroking. Nambu disassembled the gas system. The piston was scored, but everything else was fine. Replace one 5-cent part and the rifle would work for another 1,500 rounds. The rifle had not failed. A wear item had worn out, exactly as designed. On April 8th, Nambu wrote his preliminary report. He tried to keep his language neutral, professional, diplomatic. But the conclusion was unavoidable. The M1 Garand represents a significant technological advantage. American manufacturing capability exceeds Japanese capability by approximately 1 decade. Recommend immediate development of countermeasures. He submitted the report and went back to his workshop. Because he knew what would happen next. His superiors would ask if Japan could build something similar, and Nambu needed to have an answer ready. He spent the next week trying to reverse engineer the gas system. This was where the magic happened. Gas pressure from the fired cartridge pushed on a piston. The piston pushed an operating rod. The operating rod rotated the bolt to unlock it. Only then did the bolt move backward under spring pressure to eject the spent case and load a new round. It was a beautifully self-regulating system. Too much gas and the action cycled faster, but the mechanical advantage kept forces manageable. Too little gas and the action might not cycle, but there was no risk of damage. Nambu sketched out the design. Then he started calculating what it would take to manufacture it in Japan. The gas cylinder had to be machined from high-grade steel. Chrome molybdenum alloy at minimum. Japan was already rationing steel for warship construction. Every ounce counted. Next problem. The gas port had to be drilled to 0.047 inches. Japanese drill bits came in increments of 0.01 inches. They did not have a 0.047-inch bit. They would need to custom manufacture tooling. Next problem. The gas piston had to slide in the cylinder with 0.002 inches of clearance. Any tighter and it would bind. Any looser and gas would leak past and reduce efficiency. Japanese machinists worked to 0.01 inches. They would need to train workers to a higher standard. How long would that take? 6 months minimum, a year more likely. Next problem, quality control. Every rifle had to meet the same specifications. That meant inspection equipment, micrometers, go-no-go gauges. Trained inspectors who could read instruments to 0.001 inches. Japan had maybe 200 people in the entire country who could measure to that precision. The Americans needed thousands. Nambu looked at his calculations and felt something close to despair. This was not a rifle. This was an entire industrial system. The M1 Garand required precision manufacturing infrastructure that Japan simply did not have, could not build fast enough, could not afford while fighting a war on 2 fronts. The Americans had not won with superior tactics. They had won with better machine tools. On April 19th, Nambu was summoned to a meeting. The room was full of officers, generals, colonels, men who made decisions about how Japan would fight the rest of the war. They wanted to know if Japan could build a semi-automatic rifle comparable to the M1 Garand. Nambu stood at the front of the room with his report and his calculations and gave them the truth. He explained the tolerances, the tooling requirements, the worker training needed, the quality control systems, the material requirements, the timeline. The officers listened in silence. When he finished, Colonel Ishida asked the only question that mattered. Major Nambu, how long would it take to field a weapon comparable to the M1? Nambu looked at the colonel. Then he said something he had never said in his career. Something that could end his life if the wrong person heard it. With our current industrial capacity, sir, It cannot be done. Not in 5 years. Not in 10 years. The room went silent. 10 seconds of absolute silence. Then the questions started, all at once, shouting. Are you saying Japan cannot build this rifle? I am saying we lack the precision manufacturing capability. What about the arsenals at Nagoya? They can hold tolerances to 0.01 inches. The M1 requires 0.001 inches. That is impossible. That is correct, sir. It is impossible for us, but not for the Americans. Nambu was questioned for 3 hours. They brought in other engineers. Every single one confirmed his findings. They measured the same tolerances, reached the same conclusions. The Americans had a 20-year manufacturing advantage. Japan could not close that gap while fighting a war. But the officers needed options. They needed something to tell their superiors, something that sounded like hope. So Nambu gave them the only option available. We can design a simplified semi-automatic rifle, looser tolerances, heavier parts, lower performance. It will not match the M1 Garand, but it will be better than the Type 38 bolt action. Colonel Ishida leaned forward. How many can you produce? Nambu did the math in his head. We could produce maybe 2,000 per month, if we divert resources from other programs. How many M1 Garands are the Americans building? Nambu looked at the colonel and said the number that made his hands shake. 50,000 per month, sir, maybe more. The room erupted again. 50,000? Impossible. Nambu pulled out his calculations, showed them the production figures, showed them what American industrial capacity looked like on paper. The numbers were staggering. America had more machine tools than Japan had soldiers, more precision grinders than Japan had ships, more trained machinists than Japan had pilots. The math was simple and terrifying. America could build more M1 Garands in 5 days than Japan could build simplified semi-automatics in a month. The meeting ended without a decision. Nambu went back to his workshop and knew exactly what would happen. The generals would reject his recommendation. They would order production of a simplified semi-automatic anyway. It would be underpowered and unreliable and expensive. They would build a few thousand of them, issue them to elite units, claim they had closed the technology gap. Meanwhile, American factories would keep churning out M1 Garands by the tens of thousands, and Japanese infantry would keep dying at a rate of 10 to 1 or worse. 3 months later, on July 18, 1943, Japan approved development of the Type 4 rifle. It was exactly what Nambu had predicted. A simplified semi-automatic, heavier than the M1, less reliable, more expensive to produce. The first production models came off the line in February 1944. Total production by the end of the war was 23,000 rifles. The Americans built more M1 Garands than that every 5 days for 4 years straight. But Nambu's real contribution came in a different form. His detailed analysis of the M1 Garand became required reading at every Japanese military academy, not because it showed how to beat the weapon, but because it showed why Japan was losing the war. The problem was not courage. Japanese soldiers fought with suicidal bravery. The problem was not tactics. Japanese commanders adapted quickly to American methods. The problem was that American factory workers in Springfield, Massachusetts, could hold tolerances to 1,000th of an inch, and Japanese factory workers could not. Wars were not won by soldiers anymore. They were won by machinists and engineers and industrial production systems. And Japan had entered a war against a nation that was better at all three. In November 1944, Nambu received reports from Saipan. Japanese defenders armed with Type 38 bolt actions had been overrun by American Marines armed with M1 Garands. The casualty ratio was 18 to 1. In February 1945, reports came from Iwo Jima, 20 to 1. In April 1945, reports came from Okinawa, 25 to 1. Each report contained the same observation. American infantry maintained continuous fire, while Japanese infantry had to work their bolts. The M1 Garand was not just a better rifle. It had fundamentally changed infantry combat, and Japan had no answer for it. Nambu kept working until the end of the war, trying to find solutions to an insoluble problem. How do you compete with an enemy that can manufacture precision weapons faster than you can train soldiers to use them? He never found an answer. On August 15, 1945, Japan surrendered. Nambu's last entry in his engineering journal was dated August 14th. One sentence: "We lost this war in 1936 when America adopted the M1 Garand, and we did not even know the war had begun." He sat in his empty workshop and looked at his hands. Skilled hands. The best machinist in Japan. Hands that had designed pistols and analyzed rifles and calculated tolerances for 20 years. And they could not hold measurements to 1,000th of an inch. None of them could. That was the difference between winning and losing. Not courage, not tactics, just the width of a human hair. November 23, 1943, Springfield Armory, Massachusetts, 3:18 a.m. Helen Morrison sat up in bed and grabbed her notebook. Her hands were shaking, not from cold. The apartment heating was working, not from fear. She had lived through worse. Her hands were shaking because she had just realized that Springfield Armory was throwing away $68,000 every single day. And nobody knew. Nobody except her. She flipped to the first page. Tool change number 1. Receiver 21 failed inspection. She flipped forward. Tool change number 2. Receiver 20 failed. Tool change number 3. Receiver 22 failed. Tool change number 4. Receiver 19 failed. Tool change number 5. Receiver 21 failed. The pattern was there, had been there for 2 months. Every cutting tool failed at part 20, give or take one, which meant the tool started degrading at part 17, and if you changed the tool at part 17 instead of part 21, you would stop making bad parts. The math was brutal. Springfield Armory was rejecting 12% of all receivers. 12% of 38,000 was 4,560 receivers per month. At $85 per receiver, that was $387,600 per month, $16,000 per day. But that was just the reject cost. The real cost was machine downtime. Every time a part failed inspection, the operator stopped, checked the machine, made adjustments, tested again. 15 minutes per failure. Multiply 15 minutes by 200 machines, and Springfield Armory was losing 50 hours of production per day. Another 12,000 receivers per month. Another $1 million in lost production. Total cost of bad tooling. $1.3 million per month. Helen looked at the numbers and felt sick. 6 hours later, she was standing in her supervisor's office. Frank Morrison sat behind his desk and stared at the notebook like it might bite him. "You want me to tell the plant director that a seamstress who has been operating a milling machine for 18 months figured out what 50 engineers with college degrees could not figure out?" Helen did not blink. "I want you to tell the plant director we are throwing away $68,000 per day." Frank picked up the notebook, flipped through pages, set it down. "They will laugh us out of the building. Then let them laugh. While they are laughing, we can calculate how much money their laughter costs." Frank looked at Helen for 10 seconds. Then he picked up the phone. 2 hours later, Helen was standing in the plant director's conference room. There were 8 men at the table: plant director, chief engineer, production manager, quality control supervisor, 3 senior engineers, Frank Morrison, and Helen. The plant director looked at her notebook, looked at Helen. "You are claiming that all of our receiver failures are caused by predictable tool wear." "Yes, sir. And you discovered this pattern by keeping personal records that nobody asked you to keep." "Yes, sir. For 2 months. Yes, sir." The plant director turned to his chief engineer. "Walter, have your people been tracking tool wear patterns?" The chief engineer shifted in his seat. "We track overall tool consumption, sir, not individual tool life cycles." The plant director's face went red. "We are operating 200 precision milling machines. We are spending $3 million per year on tooling, and nobody is measuring how long the tools actually last." "Sir, the variability in machining operations makes it difficult to establish consistent patterns." The plant director pointed at Helen's notebook. "This woman established a pattern in 2 months with a pencil and paper. What exactly are we paying your engineers to do?" The meeting lasted 4 hours. The engineers demanded to verify Helen's data. They pulled production records, pulled quality control logs, pulled tool consumption reports. Every single number matched. Tool failure occurred at part 20, plus or minus 1, every time. The production manager did the cost calculation: $1.3 million per month in waste. The chief engineer argued that changing tools more frequently would increase tool costs. Helen did not wait for permission to speak. "Current tool consumption is 10,000 tools per month. At part 20 per tool, that is 200,000 parts. If we change tools at part 17, we need 11,765 tools per month. That is an extra 1,765 tools. At $8 per tool, that is $14,000 in additional tool cost. We are currently losing $1.3 million per month. Spending an extra $14,000 to save $1.3 million is not a difficult decision, sir." The room went silent. The plant director looked at Helen. "How old are you?" 23, sir. "What did you do before the war?" "I made wedding dresses, sir." The plant director smiled for the first time. "Well, you are now officially a manufacturing engineer. Report to Walter's department Monday morning. Your first assignment is implementing your own solution. December 3rd, 1943. First shift. Springfield Armory changed its production protocol. Every machine operator received new instructions. Change cutting tools after 17 parts. No exceptions." Helen stood at her station and watched the clock. Hour 1 passed. Her reject bin was empty. Hour 2 passed. Still empty. Hour 3. Hour 4. Hour 5. By the end of first shift, her reject bin had 1 part in it. 1 reject in 10 hours. The national average was 4 rejects per machine per shift. Helen walked to the quality control station. The inspector was staring at his log sheet. He looked up at Helen. "What did you do?" "I counted." The inspector showed her the numbers. 200 machines. First shift, 43 total rejects. Normal first shift total was 800 rejects. Reject rate dropped from 12% to 0.5% overnight. By December 10th, the results were impossible to ignore. Receiver production jumped from 38,000 per month to 54,000 per month. Quality control reject rate stayed below 1%. Machine downtime dropped from 3 hours per shift to 20 minutes per shift. The chief engineer submitted a report to the War Production Board. The War Department sent inspectors. They spent 2 days interviewing Helen, reading her notebooks, checking her math, verifying her results. On December 18th, The War Production Board issued Technical Bulletin 47-1943. Predictive tool replacement for precision machining operations. The bulletin included Helen's methodology, track tool life cycles, establish failure patterns, replace tools before failure occurs. By February 1944, every small arms factory in America was using the system. Colt, Winchester, Remington, Inland, Rock Island Arsenal, every factory that made weapons for the American military. The impact was immediate. Small arms production increased 18% across the entire American industrial base. 18% more M1 Garands. 18% more M1 carbines. 18% more Browning automatic rifles. 18% more Thompson submachine guns. 18% more Colt M1911 pistols. The increase translated to 3 million additional weapons in American hands by June 1944. 3 million weapons that would not have existed if Helen Morrison had not kept a notebook and counted to 17. March 14th, 1944. Helen received a letter from the War Department. It was 2 paragraphs long, formal, polite. It thanked her for her contribution to the war effort. It included a $500 war bond. It did not mention that her method had increased American weapons production by 3 million units. It did not mention that British and Canadian factories were now using her system. It did not mention that weapons production experts from the Soviet Union had requested copies of Technical Bulletin 47-1943. The letter said, "Thank you." Helen folded it, put it in a drawer, went back to work. May 8th, 1944. Helen's brother Tommy sent a letter from somewhere in the Pacific. The sensors had blacked out the location. He wrote about his unit getting new M1 Garands to replace rifles lost in combat. He wrote that the new rifles arrived faster than anyone expected. He wrote that having enough weapons made all the difference. Tommy had no idea his sister was the reason those rifles existed. Helen read the letter 3 times. Then she went to her workshop, picked up her notebook, started tracking cutting tool life on the next machine in the production line. Because one problem solved just meant there was another problem waiting. By June 1944, Springfield Armory was producing 62,000 M1 Garand receivers per month, best production rate in the facility's history. Helen's predictive maintenance system had spread beyond cutting tools, drill bits, reamers, grinding wheels. Every consumable tool in the factory was now tracked, replaced before failure. The reject rate across all operations was below 0.3%. The chief engineer submitted Helen's name for the Army-Navy E Award for production excellence. She was 23 years old. 2 years earlier, she had been making wedding dresses. Now she was revolutionizing American manufacturing. August 15th, 1945. The war ended. Helen's shift ended at 6 p.m. She walked out of Springfield Armory for the last time. Tommy was coming home. Her fiancé, Robert, was coming home. The war was over. She stopped at the gate and looked back at the building. 5.4 million M1 Garands. Every single one made with receivers that passed inspection. Because someone kept a notebook and figured out that cutting tools wore out after 17 parts instead of 21. 3 parts. The difference between 12% rejects and 0.5% rejects. The difference between 38,000 receivers per month and 62,000 receivers per month. The difference between enough weapons and not enough weapons. Helen thought about the inspectors who had interviewed her, the engineers who had verified her math, the factories across America and Britain and Canada and Russia that were now using her system. All of it started because she got angry watching perfectly good receivers hit the reject bin. She smiled. turned around, walked away, left the notebook in a trash can by the gate. The war was over. Time to go home. Time to make wedding dresses again. Someone else could do the counting now.